So here's our second example. Find the probability that a card chosen at random from a deck of cards is the ace of spades given that the card is black. So here we know that the card is black. The probability of it being an ace of spades, we can do this one directly. Because if you're given that the card is black, that reduces the amount of cards from 52 down to 26. Now what are the chances that it's the ace of spades? 1 out of 26. So if we can easily see how the sample space is reduced, then it's easy to figure out what it is. Okay? Now if you wanted to use your formula, probability of the ace of spades, given that it was black, well, the probability of the ace of spades and black divided by the probability of getting a black, well, ace of spades and black would be, 1 out of 52 originally, and the probability of a black one is 26 out of 52. And that comes out to the same thing. So now those first ones we could see how the sample space is reduced. Sometimes we're given percentages and it's not easy to tell how the sample space would be reduced. So here's a manufacturer that has 3 different machines that makes cabinets. Unfortunately, the machines aren't that great, and they make defective cabinets. Seems like quite often, 8% of the time, 15% of the time, and 10% of the time. Because machine 1 is the least defective, it makes 40% of the cabinets. And then 25, and then the rest would be 35%. You take a cabinet and you find out that it's defective. So we're given, here we go, we're given something. It's randomly chosen and it's found to be defective. What are the chances it comes from machine 3? So what we're going to do for these questions, we're often going to draw a tree diagram so we can see everything that happens. What happens first? Something comes out of one of the machines. So our first branch of our tree diagram shows that something comes out of machine 1, machine 2, or machine 3. That's what happens first. And machine 1 does 40%, machine 2, 25%, machine 3, 35%. Then it's either defective or not defective. Defective or not defective. Defective or not defective. And it depends on which one. We get different percentages. So machine 1 is only 8%, 92% are good. Machine 2, 15% and 85%. And machine 3, 10% and 90%. So we know that it's defective, and that's going to reduce our sample space, but we don't know how many cabinets were produced, so we don't know how many it's been reduced to. But we can still figure these things out via our formula. We want to figure out the probability of machine 3 given that it was a defective one. So we're going to look at machine 3 and defective, divide by the probability of all the defective ones. So we can see in the formula itself, this bottom part is what is restricting our sample space. It says if we divide it by only the probability of the defective ones, we're only looking at that smaller sample space. So probability of machine 3 given defective, well, machine 3 and defective, that would be 0.35 times by 0.1. That's your chances of it coming from machine 3 and being defective. Now the probability of it being defective, can you see that defective could come out of all three branches? So you're going to have three different cases that you're going to add up. Out of machine 1, 40% times 8%, plus machine 2, 25% of machine 2, and a 15% chance of defective, plus machine 3, which is 35%, and 0.1. Tally those all up. And barring any crazy calculation errors, I get approximately 0.33 rounded to 3 sig figs 335, or 33.5% chance. The formula is probably the easiest way to solve something like this. And I'll let you use the formula to figure out part B. Give you a couple seconds for that. While you're doing that, I'm going to set up a chart to show you another way of looking at this. So all right, let's see how you did using the formula. You want to find the probability of machine 1 given not defective. So we're going to have machine 1 and not defective divided by the probability of it not being defective. Machine 1, 40%, not defective there is 92%. And the probability of not defective for machine 1 plus machine 2 plus machine 3. Type that into our calculator. And I find that these ones, when you're typing them into your calculator, is a really nice place to use that fraction thing, so you make sure you have one thing on the top and one thing on the bottom. So you don't have to worry about adding brackets. All right, barring any mistake with my numbers, I've got 0.411 rounded to 3 sig figs. And if you go to your calculator and go math fraction, it changes this to 736 out of 1791. Now, the reason I wanted to do that, that's an exact answer. So if you wrote your probability as a fraction, you could write it as an exact answer by changing your decimal back to a fraction. Now, what I did over here on the right is I wanted to show you why these numbers come out the way that they are. So I picked an arbitrary number. I suppose the company made 10,000 cabinets. If they made 10,000 cabinets, because machine 1 does 40%, machine 2 2,500, machine 3 3,500, 35%, you could figure out this far column to begin with. 4,000, 2,500, 3,500 would be the totals for machine 1, machine 2, and machine 3. And if I knew machine 1 did 4,000 cabinets and 8% were defective, 8% of 4,000 means 320 are defective there, and 3,680 are good. Same thing, machine 2, I could figure out how many came out defective there, how many were good, how many were defective from machine 3. So if we do our totals here, we see that there's only 1,045 defective in an entire day. Most of them come from machine 2. Machine 2 produces more defective ones than any other one. If we do machine 3 and defective, because that was our first question, right? Which we got 0.335. If we do 350 divided by 1,045, we get that exact same number. If we wanted to do what we did second, probability in machine 1 given not defective. Well, not defective reduces our sample space from 10,000 down to 8,955. And machine 1, if we do 3,680 divided by 8,955, we get exactly this same number. And we can reduce that fraction to 736 out of 1791. So if you want to, you can pick an arbitrary number and make a chart to figure out how the information that you're given reduces the sample space to a smaller number. Sometimes, though, depending on the percentages, you have to pick a really large number in order for your numbers to turn out nice. Like if you just did 1,000 cabinets, you might not get nice numbers because you would get 37.5 defective cabinets. It'll still work to use that decimal, but it doesn't make as much sense. Well, of course, if you got half a cabinet, it's defective. It's not going to be very good. But then you technically would have half a cabinet that was good, which would be confusing. So that's another way that we can look at our conditional probability. I find that using the formula is quicker because making a chart like that takes some time. I find making the chart makes a lot more sense than using the formula. So there's some things to think about.